everybody get out that blue free body diagram thing?
Oh, the blue one?
Yep. Everybody's going to do one on the board. How many we got? 1, 2, 3, we got 18, we got 17. We only have 21 people. Now we have 19. So almost everybody's going to do one.
Oh, yeah, food.
All right, let's go down the row. Vivian, you're going to do number 2 on the board. Lauren, you're going to do number 3 on the board. 1, number 4. Huh? Okay. Kennedy, number 5. Selena, number 6. Bontami, number 7. Oh, number 7. Lisa, number 8. Colin, number 9. David, number 8. 10. Go backwards in time. Marcos, number 11. James, number 12. Melanie, number 13. Lucy, number 14. Christian, number 15. Nia, number 16. Ian, number 17. Who haven't I picked yet? Okay. Jonathan, number 18.
Can I switch with Kristen?
All right, go. Onto the board.
He didn't get
I
in.
think we're all done. Okay, where is number 1?
In the back.
Number 1's in the back?
Yeah, no.
So yeah, nobody had number 1. All right, so let's start right here then. Number 2, where's number 2? Number 2's in the back. Let's do all the ones in the back first.
It's in the back. Go.
Flip it around.
Oh.
Camera first.
All right. Here we go, number 2. Everybody, okay, remember, when you're doing free body diagrams, or when we're doing force problems, right? Free body diagram, very first thing you do, and if you don't get your free body diagram right, there's no way you're going to get the rest of the problem right.
There, cow.
See, this is why
What? I'm not in the front anymore.
you're so easily distracted. Okay, so here we go. Our very first one. We have tension up and we have weight down on our rock. That's it. Very nice. Smiley face. All right, number 14. Rock flying through the air. How many forces?
1.
Yeah, all we have is the weight down and that's it. Very nice. That's it. There does not have to be a force in the direction it's going. Right?
Which number is that?
That's number 14. Okay, I'm jumping around. Number 4. Our
Melanie.
Melanie. So now we have force of gravity down. Now notice you can write it force of gravity. You could write it weight. You could write it mg. There's lots of ways you can write that. Or you could, I guess those are the major 3 ways you could write it. Down, straight down, and you have 2 tensions. Now in number 4, the angles up here are the same. So tell me, if these 2 angles are the same, what does that tell you about tension 1 and tension 2?
Equal.
They must be equal. And what's really important about this is if they're equal, and this thing is static and not moving, then that means the forces to the right and the forces to the left have to be the same. And the forces up have to be the same because the angles are the same. And these 2 must each be equal to the weight over 2 then, right?
Yeah.
Okay? All right, number 8. There is an object. This time it's a person. Sunlight coming off Mr. Bruin's head. What the heck?
Whoa.
All right. Gravity down. I'll agree with that. And then we got a normal force this way. You agree with that?
Yes.
Okay, and then I have 2 forces here. What's this? FB. Force from the block. What would we call that force?
Normal.
That's also normal. So this is the normal from the incline or whatever this is. This is the normal from the block. So there are 2 different kinds of normals, 2 different ones. So force from the floor, normal force from the floor, normal force from the block. And then friction, is this
It
frictionless?
doesn't say if it is or isn't.
It's in equilibrium.
It's in equilibrium, so no.
Okay, is friction necessary for it to be in equilibrium?
No.
Okay, we could get by without friction, all right? But might there be friction? Possibly, but if there is friction, it'd be static friction. All right, number 16. 16 is rock tied to a rope, pulled straight up and accelerating. Okay, so what's the difference between this one and this one? Okay, this one the acceleration is 0. This one the acceleration is not 0. It's accelerating up. So how do I designate it being different?
That one's bigger.
Very nice. This one's bigger than this one. Whereas over here, these are the same. Okay? Because if it's not in equilibrium, then one has to be bigger. All right, number 13. Number 13, a rock is decelerating. Ooh, I hate that word.
I
It's
know.
accelerating to the
I need to
left.
put an arrow with like huge exclamation marks by it.
Yeah, that's the one bad word on this. The rock is decelerating because of kinetic friction. So the rock is moving to the right, but accelerating to the left, is the way we like to express that. Okay, so normal up, weight down, friction to the left. Looks nice. And what kind of friction is that?
Kinetic.
Kinetic. So if that's kinetic friction, are we allowed to use this?
No, yes, no.
Force of friction? Well, yeah, I mean, it's the same for all of them. It's just
For
that-
kinetic, right?
Yeah.
Now if it was static friction, then we'd have the less than or equal to sign, that would give us problems, right? And can I just write this then? Is that okay?
Yeah.
Because it's not accelerating up or down, so therefore these must be equal. In this case, right? Okay. What about number 17? 17 is a rock is tied to a rope, pulled so that it moves horizontally at a constant velocity. Note, there must be friction. Okay. If there's no friction, can this thing be moving to the right at a constant velocity?
No.
If there was no force on the rope.
But then it would, I guess its constant velocity would be 0 to the right.
Well, unless you
Unless you pushed it and it had no friction, so it stayed
Ah, I
out.
guess that's true.
If there was an initial push.
Yeah, can these two forces, the way they're written, cause equilibrium?
No.
Uh-uh. Okay, so if it's going to be in equilibrium, these two are going to add up to be something down here somewhere, right?
Yeah.
And if it's moving to the right and there's friction, then the friction would be this way. And that must be drag. Now, we won't actually solve for drag. Occasionally, very rarely, it shows up on our exam. But when it does, it'll be a problem like this. They'll say, well, how big does the drag force have to be? Well, the drag force has to be equal to this part, right? So that part of the tension is equal to the drag force. And the upward part of the tension would equal the weight, right? So the weight over here, and the force friction here, and that's equal to the tension, and you'd have an angle and you could relate them all. Okay? You could find it that way. Does that make sense?
Yeah.
Okay. All right, and then,
That was it the other day.
all right, we'll assume that the acceleration of the penguin is 0. This was number 10. Number 10, a rock falling. Ta-da! Done. Very
Oh,
nice.
that pan pigeon.
Number 12, yes.
You didn't do the heavy basis factor. You didn't finish it.
All right. To all of you that did a correct one back there, which was everyone, happy face. All right. Oh, happy face. Which one is it? Number 12. Number 12, rock falling at a constant terminal velocity. Ooh, terminal velocity. The only way for you to fall at a constant velocity is if,
Drag equals.
yeah, you got some other force up that equals the force down, right? Now remember, when you draw your free body diagram, don't forget, try to draw all your forces attached to it, not off to the side.
I had to draw the little thingies.
Number 6, a rock sitting on a table in equilibrium. Normal force up equals weight down. Very nice. Number 15. I draw a smiley face, but it already has smiles. So I'll put freckles on it. All right, number 15.
Oh, he's trying to be.
Right,
That's a good
rock
one.
flying through the air. It's at the top of the parabola. Okay,
Down.
rock anywhere flying through the air, as long as there's not too much air resistance, they all look like that, right?
Yep.
Weight down, so it's accelerating down. Okay, number 3. Number 3 is friction prevents sliding. Hey, normal force, weight, friction. Looks good. They're even broken up into components. Now we're going to talk about this. Okay, this one's in static equilibrium, right? Okay, if it's in static equilibrium, since the acceleration is 0, since the acceleration is 0, you can put your coordinate system any way you like, because it doesn't really matter, because the forces are going to cancel out in any direction. Who drew this one? Okay, you can pick your coordinate system however you want, and x, y was what was chosen, right? Which is fine. That means that I've got a horizontal force here and a horizontal force here, and they must cancel. Perfect. And then I've got an upward part of the normal and an upward part of friction that cancels the weight down. Excellent. Okay? You could also break this one up like this if you wanted to. That's another convenient way to break it up. It's up to you. It doesn't matter. Okay? If you break it up this way, then you'll have a component here and a component there to this one. This one will equal that, and this one will equal that. So you can do it that way as well. Either way. It doesn't matter since it's static. All right, number 7. Rock tied to string on incline. Okay, that and that are exactly the same. The only difference is that instead of friction holding this one back, it's tension holding this one back. So they're both exactly the same. Okay, number 9 is rock sliding down frictionless incline. So this one and this one, number 3 and number 9, are all the same except friction disappears. So therefore, this one's going to accelerate. Now, which way is this one going to accelerate?
That.
Down.
Right.
Down?
No,
This way.
Okay, down the incline, right? So it's going to accelerate that way. How are we going to set up our coordinate system to make life easy?
Make it diagonal.
Yeah, make it diagonal like this. So therefore, we split it up like this. That part cancels that part because there's no acceleration this way. All the acceleration is that way. So this is the part of the weight accelerating it. Okay? All right, number 11. Hey, nice cubical cow.
Yeah.
Number 11. Rock is sliding at a constant speed on a frictionless surface. Okay, so normal force, weight, got to cancel. Sliding to the right. So do we need a force to the right? No, you're very good physics students. Okay, don't be decoyed by the motion. Only the acceleration matters for forces, right? So since it's not accelerating right or left, there's no need for any forces. There's no friction, so that's it. And number 18, way down here. Rock is tied to a rope pulled so that it accelerates horizontally at 2G.
Where's my smelly face, please?
Right, so weight down, tension this way, and it's not accelerating up or down, correct? Just to the right. That means the upward part of the tension must cancel the weight, and this horizontal force is what's accelerating it to the right. That part of the horizontal force. Okay? Looks good.
Number 5.
Where's number 5?
On the end.
Oh,
Okay, B-I-O.
sorry. Number 5. Oh yeah, number 5.
Oh, wow.
Number 5. Okay, a rock held up by 2 strings. The strings are not at the same angle. Okay. Trick question again. Which tension is bigger?
The one
Same.
closest.
The one closest, they're both touching.
Two
This
on
one right
one.
here. This one's left.
Okay.
It's upward.
Since the horizontal forces have to be the same, since it's not accelerating, then the only way for that to happen is for this one to be shorter, right? It's going to be a tiny one. So now these are equal, and so my upward two forces equal the weight down. Okay? Excellent.
No!
I think one of your e-homeworks is like this. Let's say that I have a force right here, F,
Which e-homework are you playing?
sliding this across the tabletop, and there is friction.
It's
Okay.
Richard.
I want you to set up the free body diagram, set up the coordinate system, and set up your F equal ma for your two separate directions. Here, we'll make it even more grand here.
One.
Call this F1. We'll just start with this, F1. All right? We'll start with this. All right, draw the free body diagram. Yeah, it's like number 2.
Yeah.
It's like your e-homework number 2.
Sequence is a
Go, go, go.
right? So
Yeah,
think
come
of
on.
a
Free body
low-
diagram.
a lower word
Okay.
than
Step number 1, free body diagram.
like that. Right. That's close, but that's not the word you want.
Is it accelerating? Set up your coordinate system. Build F equals ma for two directions.
Okay, Mr. Bruin.
And then, only then, do you solve. All I'm asking you to do is get all the way to step number 4. Just build your F equals MAs for your two directions that you pick. Then we had a great question. The question was, is a force like this the same as a force like this? And the answer is yeah. It's exactly the same.
Good, 'cause that's like two.
Yeah, so if you want to redraw it, because I usually like to draw mine so the forces go away, but some students don't like this because the force is going into the ground. It doesn't matter. Okay? So whichever way you like to see it, you can redraw it however you'd like. Because occasionally you'll see it drawn this way, so I drew it that way. I haven't told you whether it's accelerating or not yet. There is friction. But if it will accelerate, it'll accelerate that way. So how should you set up your coordinate system?
Well, that depends on.
X, Y is going to work great. Because that'll handle every possibility. Even if acceleration is 0, that'll still work, right? So forces, what's it going to look like?
Weight down.
Weight down,
Normal up.
normal up,
Friction back.
friction back. Looks like that, all right? So, now, let's color code this at first because it helps a lot of students. So let's make our X and Y different colors. We'll make X pink, and we'll make Y,
Yellow.
can you see yellow?
I don't think so.
Can you see that?
Yeah, I think.
All right, that's actually a pretty nice yellow marker. All right, so if I redo these, then this one's a pink. These two are yellows.
What is F1? Oh my God.
Okay, what is F1?
It's pink and yellow.
It's a both. It's a yellow and a pink.
Wow.
And a peak. Oh, triangle.
And so, we got a triangle. So we need an angle. So here's my angle theta. So what we're going to do is we're going to build our pink and our yellow equations. All right? We got our X, which is pink. We got our yellow, which is Y.
Can't configure it backwards.
All right, so now I'm going to do my equations. In the X direction, how many forces do I have?
2.
2. Okay, which way is positive?
We'll say that way.
That way, right? So, I got any positive forces? Are they all negative? What are they?
One positive, one negative.
What's my positive one?
The F1 cosine theta?
It's the F in the X direction, this part right here.
Yeah.
But that's going to be F
F1
cosine theta,
cosine.
right?
F1.
Oh, sorry, F1 cosine theta, sorry. So it's F1 cosine theta,
And then force of friction.
and then minus, because it's in the opposite direction, force of friction equals, is that all my forces, right?
Yeah.
That equals MA. There you go, that's how you build it. Now, if on the test you want to bring colored pencils or whatever to do just what I just did here, bring it on, okay? Because eventually, after a little bit of practice, you'll do this in your sleep. Okay, yellow. Okay, tell me, F equals MA in the Y direction. What's this going to look like?
F1.
0. What's 0?
The Y forces. Some of the
Zero
forces
times-
in the Y direction.
Why do these have to add up to 0?
Because it's not accelerating
Because it's
neither.
not going to accelerate that way, right?
Yeah.
So if you want, technically you should say all the ups minus the downs add up to 0. But most students skip that step and they just say all the up forces equal the down forces. Okay? So how many ups do I have?
2
What are they?
and
Yeah, 3
F sine theta.
equals M.
This part right here, which is F sine theta, F1 sine theta, right?
Down.
It's going down.
No, it's going. It is going down. It is
Ooh.
going
Told
down.
you, fools.
Hold your fools.
Told you, fools. Told you, fools.
Told you.
All right, that one's down. And this one's to the right. So we got that on the wrong side.
Hard with it.
Oh no, it's a redo. Okay, so here's all my ups. I just got one. And that's going to equal all my downs. So I got that F1 sine theta plus
MG.
mg.
Okay, I have a question though.
Yeah,
Because you said originally you didn't know acceleration, but you just assumed it to be positive. Right?
I assume, look, if it's going to move, the only way it's going to move is that way. Correct?
Yes, exactly.
Okay, so here's my question.
But if it were moving at constant velocity, which you don't know, hang on.
Let's look at all the possibilities. Okay, everybody? This is correct. Assuming that there's acceleration. If there's acceleration, it looks like this. Okay, so assuming acceleration that way, it's going to look like this. What kind of friction is that? Kinetic. Because it's moving. So here's my question. If it's moving to the right, accelerating, that's kinetic friction. Can I do better then with this equation? Can I make this better? How can I make it better? Because I know what that is. Force, friction, kinetic equals mu force normal, right? So I can put in F1 cosine theta minus mu normal force equals ma. Can I make that better?
The normal is mg.
Uh-oh.
No, it's not. No, it's
You
not.
can plug
It's
in
mg
that.
plus f sine.
All right, now I was hoping somebody would say that because that's what we almost always jump to the conclusion, that normal equals mg. But in our case, does normal equal mg? I guarantee you on the exam, I'm going to give you, and I guarantee you on the AP exam, that they'll have some sort of problem like this, where they're going to see if you plug in mg right here, or whether you plug in what it really is, okay? Guarantee it. So in our case, that's what normal is. So I plug that in. So look, my equation's getting,
Bigger.
unruly, but not unworkable. Minus mu, and that's all times F1 sine of theta plus mg equals ma. Now I'll tell you, if you want to get full credit on the AP exam, you're going to write down, in fact, what's probably best for most of you to do is to write F equals ma in the x direction, first equation, and then
Some of
you
the forces in the x.
and then you put in what your x's are, and then you put in, if you can, like we did here, friction equals this, but normal equals that. And just put it in step by step. Guarantee you'll make fewer mistakes, guarantee you'll get a better grade. Because what happens is the students will start plugging numbers or something in here, right here, and you'll make some mistake, and your number won't be right because you just plugged in the wrong number in your calculator, and they can't give you these points in between. Okay? They give you partial credit if you show your work. And the best way to show your work is to show it in symbols and then plug the numbers in at the end. The absolute best way to do it. And fewer mistakes, and you'll find out it's easier too, because sometimes a lot of this stuff will cancel out, and you're in good shape. All right, so if it's accelerating, we can find the acceleration now. Because all we got to do is take that, divide it over here, and you got acceleration, right? Okay, now let's take a look at this. What changes, let me put it that way, what if it's not accelerating and it has a velocity that's constant? Does that change anything over here? Everybody okay with that? That stays the same? Because we didn't change anything in the up and down direction at all, did we? What we changed was the acceleration. Now the acceleration is 0. Okay, so what does that change over here? Yeah, this is now 0, so that's 0, so that's 0. Do we still have kinetic friction?
Yeah.
Yeah.
But it's equal to
But
the
it's
x
equal
component.
to,
So now what we could say is that this is equal to that, right? Or we could say this minus this equals 0, whichever way, but most students prefer to say this minus, or this equals that part there, right? Okay? You can change it again. What if the acceleration is 0, but this time it's at rest?
no.
What changes now?
Well,
It's static friction, not kinetic.
Oh.
Up and down, is that why some of the forces in the y direction is 0?
Say it again?
No, it's okay. You answered my question.
All right. Okay. If it's at rest and not moving, does this stay the same?
yeah.
Yeah. This changes to static. So, can I do this now?
No.
Oh, everybody watch. Force, friction, static. Less than or equal to mu force normal.
So that's assuming you have the same.
Danger, danger, danger. Less than or equal to. You can't just take this and chunk it in there because it's not equal to it. Could be less than that, right? So, the only time you can chunk this in here is if you're at the maximum value. So how could they word the problem so that you knew that you could just chunk this straight in here?
Right
Okay,
before in motion, right before.
Yeah,
movement,
like
maximum required.
What's the maximum force that you can apply and it's still not moved? Or what's the minimum coefficient required to keep it from moving? So then you're at this maximum value and it's going to just start to move and then you can plug this in. It's okay then. Yes.
The static friction is when it's still on the kinetic friction, so it's moving, right?
Yes.
Okay, but you said the static friction is less than or equal to, but what if it's equal to? What do
Okay.
you change to 50?
Good point. Very nice. Now, we haven't talked about this yet, but kinetic friction and static friction, let me put it this way. That one is bigger than that one.
Yeah.
In fact, you're probably going to do a lab. Oh, no. I don't know if you'll do this lab or not.
We already did.
Did you already do it? The one where you pull the thing, pull the block, and when you pull the block, like it'll do force versus time, right? And the force goes up and up and up and up, and all of a sudden it breaks free and it starts to move, right?
Yeah.
That's your static friction, and that's your kinetic friction. The kinetic friction will be less. And the reason why is because if you think of atoms and the imperfections in the object, when they sit there, they kind of wedge into each other a little bit. It's hard to break them free, but once they break free, they kind of bounce over the top of each other, and it's easier to move them. And some of you have noticed this too. You've ever tried to push something across the floor? You ever tried to push a car? What's the hardest part about getting a car moving?
The initial part.
Is the initial part of getting it moving. Because that's bigger than that.
That's why you pay more gas when you try to go back.
Why you pay more gas when you stop and then try to start up. Well, there's other reasons too, but when you're trying to push something, don't let it stop if you're trying to get it somewhere. Because once it stops, you got to start it all over and break free again. right? Okay, so you just see the three different things they could ask you. It could be at rest. It could be moving at a constant velocity. It could be accelerating. Okay, do this one now.
Oh, I
You
hate
guys are
that
not a
one.
safe
What?
situation.
Are you serious?
That one's in our homework.
Is that a wall?
That's a wall.
That is not.
It's a line drawn in green marker.
Wait, so what I asked him,
How would you draw the friction in the
look, Mark,
weight?
Oh, it's kinetic, so it is moving.
How would you draw the friction in the weight? Is there friction?
All right, so we'll assume it's moving upward, velocity equals constant.
How would you draw friction and weight?
All right, follow the rules. Okay, remember the rules. Normal force always acts which way?
Opposite to the surface.
Perpendicular to the surface. Okay, friction always acts which way?
Against motion.
Against the relative motion of the two. So since this one is going to try to slide up, friction is going to be
Down.
down. All right, parallel to the surface. Gravity is always
Down.
Down.
down. All right, so you just draw them. How they
It could be upward if you were below the.
Which arrow overpowers the other?
overpowers the upper.
Other. Like which one's on here?
Well, we'll find out. Let's draw. Well, its velocity is constant, right? So all the forces have to add up to zero, because it means acceleration is zero. All right, so what forces do we have?
Normal.
Which way?
To the
To
left.
the left.
Horizontal.
Normal. What else we got?
Friction.
Friction, which way?
Down.
down.
Down. What else?
No,
You got
gravity.
MG going down.
Gravity, mg going down.
They're equal.
And then you
Anything
got-
else?
No.
You can draw
Not
like that.
relative to
So
the.
I drew.
Ah, okay.
Well, you got the. If you want to split force into X,
Yeah,
Y,
that's what I'm
but
saying,
you
split
don't.
force.
Okay, now, everybody, if they ask you to draw a free body diagram, don't split this up. Just draw the force. That is the force, right?
The force.
Maybe.
Duh.
All right, is it accelerating?
Now.
No. Okay, is there any preferred way to draw our axis then?
Just do X, Y.
Is x, y going to be okay?
Yeah, because that's
Yeah,
where
'cause we
motion
got
is.
most of them are x and y. So we're going to do x and y. We're going to do just like this, x, y, no acceleration. So the sum of the forces equals ma in the x direction. The sum of the forces equals ma in the y direction. So what's this one going to look like?
Which one?
This one.
Normal.
Okay. Yeah, no.
So I got a normal, positive or negative?
Negative.
We'll
Negative,
say-
normal, what else?
And the X component.
Okay, so we need the x component of this. We need an angle, right? So why don't we call this theta this way? So if I call theta that way,
Use F sine. Degrees.
48 degrees.
That was fine.
Well, if you do, well, we could do it the other way.
Why would we pick a random number?
In that case, it'd be sine. X would be a sine.
So the way I've drawn mine,
Makes it
the x component is going to be sine. So F sine theta equals ma. Can I do better than that?
Just pick random numbers.
Yeah.
I can do better. What did I do that I can do better on?
solve
Which
for the
one?
normal, which is equal to that.
Put,
Just like
put that sign at the beginning.
Normal is equal.
Thank you.
Oh.
The acceleration is 0.
It doesn't make-
So that means normal equals F sine theta. Because it's not accelerating. In fact, what we should have done to begin with to make life easy is to realize, hey, there is no acceleration. So that's 0, and that's 0.
Both zero.
Okay, I was just waiting to see if anybody could spot it. Okay, what goes over here then?
All your y forces.
All my y forces.
Friction, gravity.
Well, negative gravity, negative friction. Okay, equals the y component, F
F
we'll say
cosine.
Fy and then convert or whatever.
All right, you could have put these as negative if you liked.
If you flipped it.
Yeah, well, what some students will do is they'll do this. This is fine. Which is a correct statement, right? Because MA is 0. I just skipped that step and went to that one. Most of you will do that anyway.
Then
probably.
we just simplify force of friction.
Okay, force friction. Static or kinetic?
No, kinetic.
Kinetic, yay, kinetic, happy face, right? We love kinetic friction because then we can do better than this. What can we do?
Plug it in.
Plug in N.
Mu F of
How about mu normal, right, equals force cosine theta, and then I can plug in for N,
I
right?
said plug it in, not plug it in.
Ah.
Okay, making sure you said that. Make sure you caught that.
All right, because this plugs in right there. And now can I do any better?
And um,
Or are we done?
I think we're well. Let's see. Hold up.
I think we're good.
We're solving.
Yeah, what are we solving for in our
I don't
problem?
know what the
I don't
question
know.
was. I think we're solving for
Force
friction.
of friction.
Force of friction. So solve for force of friction.
Hey, now look, if we're solving for force of
You didn't even have
friction,
to simplify it.
I could have stopped right here.
But
Yeah.
we are overachievers.
Yeah, so, yeah, we are overachievers.
We blame.
So, yeah, just particularly on multiple choice questions, but also on free response, it's important to look at what are you trying to find, right? Looks like we were trying to find that, so we went more farther than we needed to go.
Thanks,
Wait,
bro.
hold on, hold on. I
More
got to
farther?
feel it.
More farther.
Really?
Me English speak.
Why did you do it? Wait, what do you velocity equals constant from?
It says that it moves upward, but it doesn't give us the acceleration, so we have to assume it's,
Wait, hold on.
Acceleration of gravity is not
that's true, but that's just the acceleration due to gravity, it's not necessarily the free fall. They were just asking for the force of friction,
That's all.
and so, since we knew F and we knew mg and cosine theta, we can stop right here and solve for what we needed in that problem. We just went a little bit farther in ours.
We were just in the mood
Okay.
of simplifying.
There's another one in there where you push the object across the ceiling.
Yeah, pretty.
Okay? All right. There's also like a helicopter problem, and there's one like a ball hanging from a string in the back of a truck or in a car, right?
I didn't like that. Those two.
Actually, it turns out that once you see how they work, they're not that bad.
They're not
Okay.
hard. It's just that I didn't like the way.
You don't like it.
Think about this.
Because
If
one
we're
had
in...
acceleration, the other one doesn't. It was like.
Nah.
Which one?
All right, let's say I hang an object from the ceiling, okay? And it hangs from the ceiling, and it's going to hang straight down, right? Okay, but let's say that this room would accelerate that way.
Whoa.
What are you doing?
We're in a
We're
room
in a room.
on wheels
Wait a
On
minute.
the wheel.
Yeah.
with a rocket motor in the back.
Yeah.
And we hang a student from the ceiling.
From the. I'd say head, but
Yeah.
Rocket motor on the back.
Hey, that's like Buzz Lightyear.
what?
And we hang a student from the ceiling.
That first one.
Haha.
That looks so bad.
Now. What? You're taking things wrong.
Make it a noose. Don't leave it as a regular rope.
They have a helmet on that's suspended from.
Wait a minute,
That's
Phil.
not much better.
Yeah, it's no on the force of the neck. The battery.
I guess.
Is the helmet
It's a
drilled
big
into
plunger.
Is
That's like-
it drilled
The
into the
first toy
skull?
No, it's just a plunger.
When they're, it's like the
Well, that
first
only
toy
works
when
on
they're
the
on that
computer
rocket
head,
and
then.
they're trying to get into the
That's
18
right. Okay, now, look, if the room is stationary, then the person hangs straight down. But if the room accelerates to the right, okay, think about it for a second. If you're hanging from the ceiling and all of a sudden the room begins to accelerate that way. Now look, does your body go that way?
Yeah.
Really?
No,
the body
like, your
stays in
feet, your
place.
feet do.
Goes along.
Okay, here I'll give you another example. Okay, any of you ever been in a car crash where you're hit from behind?
No.
Yes.
You
Yes. Oh yeah.
All right?
You're like.
I guess I forgot.
Okay, and here's the deal. You're sitting in a chair.
And you swing back like you get
You're sitting in a chair.
I run up
You're-
and kick the chair.
Yeah, a car comes up, hits the chair. The chair goes forward because the car is pushing the chair forward. I go forward. Let me back up. I don't go forward. My body goes forward because the chair pushes my body. I got nothing here pushing my head forward. So what does my head do? It doesn't go back.
It stays in
It
place.
stays in
Relative to
place.
the ground.
That's what I said. I said your body stays in place, but your head moves around.
Yeah. What happens is your head has mass. It has inertia. Now, if you're sitting in the car, it looks like the person's head goes back. The person's head does not go back. The person's head stays put, and their body goes forward, leaving their head behind. Okay?
So an accident can just say, dang.
But still, their feet.
Well, that's immediately at collision when there's immediate acceleration. But if there's
The person's head never goes back. The person's head sits there. And then what finally brings the person's head forward? Because the person's head normally does not end up in the back seat.
Your body.
Yeah, your spine, your neck yanks your head forward only after your neck has had tension in it.
and then it comes back.
All right, so why do you need a headrest? Why do you need a headrest?
We'll go for it too.
Yeah, so that you have something to hit the back of your head to drive your head forward.
That's why they leave a gap for your neck so it snaps in half.
You should have a seatbelt that goes
Yeah,
like
so your neck ends up in the back seat, and your head drops down.
It's not biology.
All right, now look. Same thing here. When the room goes forward, the person stays put, and the only thing that drags the person forward is the tension in the rope. So the person ends up like this. Okay? And so you end up with tension and mg. But which way are you accelerating? That way. So how do we set up our coordinate system? Like that. And so we split these up. And so mg equals that because there's no acceleration up and down. And we end up with this part of the tension yanking the person along. Okay. Now, that's the one with the car with the ball and the string. There's a helicopter problem. In the helicopter problem, you have your helicopter.
Good helicopter.
The helicopter is dragging something behind it through the air. But in this case, the helicopter is going at a constant speed, I believe. And if you're going at a constant speed where the acceleration equals 0, then what happens to all the forces here?
It's already caught up.
They cancel out, right? You got tension, you got mg, and then you got to have something else.
Air drag.
Yeah, you got air drag, and the drag is in the opposite direction you're going. Now in this case, these three forces cancel. Okay? All right, how are we doing? We doing okay?
Yeah.
Okay, incline.
I like that intro.
All right.
That's the only one I did.
Oh, this is where the next one. Rudy, I said something. Rudy.
All right, let's do friction. Let's say there's friction.
Number 2.
Rudy. We'll probably take
All right,
it.
so everybody, draw the free body diagram of this one. This is problem number 2.
Is it?
Do we gonna draw it too?
Well, there's more than one like that.
Yeah, there's several of them. Sorry.
It's the one with friction, we'll say number 2.
Rudy,
Because it gives us both the
it's like
stack
my
and
intro.
the
Intro.
Yes. Okay, let's say there's friction. Let's say that there's static friction, and let's say there's kinetic friction. And we will solve two different problems. But the very first thing, no matter what, you still have to set up the free body diagram.
They already did it.
Forces. Forces.
It's because
Gravity.
mg.
Normal. Friction.
Normal. Okay, now, everybody, if it's going to accelerate, which way? Down. That way. So how do we set up our coordinate system?
That's why.
That's right.
Parallel and perpendicular. It's easiest. Okay, now, that means that if we have an angle theta here, then, okay, follow the logic here. This is 90 right here, right? Everybody?
Yeah.
You see that? What angle is that?
the same as the
They
180
equal 90
minus
added.
90. So it's 90 minus theta.
90 minus theta. All right? Now, if I draw a line down this way, you see this? From here to here? That's 90. So what's this angle?
I don't know. Let's see.
If that's 90, and that's 90 minus theta, that makes this theta.
Yeah.
Okay, so every time you're on an incline like that, this angle right here is going to be it's going to be theta. The same theta as this theta, okay, by geometry. So,
Perpendicular to the.
here's the hard part for
Gravity?
most.
Give Mr. Beal.
It's going to be along the same line as the normal, perpendicular to the surface. Draw that line
Oh,
like
yeah,
this.
That's what I meant. Bring it to
Yeah,
the
yeah.
surface. Okay.
Now, here's the deal, everybody. How do I draw this triangle right here? Do I draw it like this,
No, you should do the other way.
or do I draw it like that? Which one?
Oh. Like that.
That like that, yeah, because you want to have a
Like that, you want
right
it equal
angle.
to the
Okay,
X.
which one is the hypotenuse?
The-
Is it this side, the
Yeah.
hypotenuse, or this side?
No, the other side.
This side, right? MG is the hypotenuse.
So you can't be
So you
perpendicular
can't
to
have
it.
this one bigger, right? So it's got to be like that. There's your 90. That's kind of hard for students to draw at first. Okay, if you're having trouble with that, if you have trouble drawing these, here's what you do. You look at it, and you turn your head. Or easier yet, you take your paper, and you rotate it.
That's what I do.
That's
Actually, the first couple times you do it, it's hard to see. So just rotate your paper. Okay? Yeah. Piece of cake. All right, now, then let's build our F equals MA in the parallel direction first. What do we got? How many forces do we have in the parallel direction?
by X, that's what you mean?
I got, no, not X, parallel. Parallel to acceleration.
That's all right.
Um,
We define
force
that
of
as X.
friction.
You're trying to confuse me.
Force of friction, is that positive or negative?
Negative.
Negative force friction. What else we got?
That line is
Plus
bottom.
that.
That one. Well, what do we call that one?
That's the X component
It's
or
the
the parallel
MG
component.
parallel to the plane. Not X, it's not X.
We defined it as X.
Stop it. All right? Or it's going to be MG,
Sine. Cosine.
which one? Tangent? Cotangent.
Tan.
Cosine.
Cosecant? What is it?
It's a trig function.
Oh,
Which one is this?
I gotta put my AOH.
Which one are we showing?
This side, right?
Sine, yeah.
So I got MG sine theta. Any others? Is that it?
Yeah.
Equals MA in the parallel direction. Okay, what kind of friction?
Kinetic, because we have acceleration.
Kinetic. Well, maybe.
Well, let's find out, because what are we asking?
Okay, so let's just leave it here, question mark, and we'll figure it out in just a second. Okay, the sum of the forces equals MA in the perpendicular to the plane direction.
Why you draw it like that?
It's the way you do it.
Why can't we do X and
X and Y. X and Y is for babies.
We are babies.
Your physics babies.
Yes.
All right, what goes in here?
Normal.
Normal,
And NG cosine theta
MG cosine.
plus or minus?
minus.
Equals what? Zero, because we're not accelerating that way. That's the whole point.
We're not levitating perpendicular.
So,
to the plane.
most of you will just skip that and write N equals mg cosine theta. And you'll mark it on your drawing like that. Okay? All right, now, here's how we go about solving this problem depending on what they ask. If they ask for, well, what is the acceleration? Then what did they just tell you?
Yeah, it's moving.
That it's moving, so therefore this is kinetic. Therefore, we can plug in what?
Oh, well,
That thingy.
MG cosine.
Mu normal, right?
Yeah.
Because force of friction equals mu normal if it's kinetic. And then we can plug in for normal, not mg, but that, right?
Yeah.
So we get mu mg cosine theta equals ma parallel equals mg sine theta. Okay, so now tell me this one. what if the question is something like, the box is just sitting there and not accelerating, and they ask for how big is the static friction?
The force is
Do the force.
What's the force of friction for it to be static?
And that,
less than equal to
S is equal to the
mu and
gravity of the.
Yeah. If the acceleration is 0, if it's static, then you get mg sine theta minus force friction static right here. But that equals 0 this time, right? So what's the force of friction equal to? Force friction static is just equal to mg sine theta, right? Does that make sense?
yeah.
And I don't plug in mu force normal because,
You don't want you just want.
yeah, I don't want to know what it's less than or equal to. I want to know what it's equal to. It's equal to that one. All right? All right, what if they ask the question, go ahead. The question? Why thought somebody had a question?
No, I was asking for number 2, since it was asking for the frictional force. You just use that equation right there and solve for F of friction?
Yeah. If it just asks for what the frictional force is.
Not that one?
Well, no,
This
it's
one?
not static though. We're just saying that it's still.
It-
Oh, okay.
yeah, if it's static, then this is for kinetic.
That's when it's in motion.
That's
The
when it's
other
in
one-
motion. This one, if it's just sitting there, because we can't go any further than that. Now, what if they ask you a question like this? What's the largest angle that you can have this incline
Before it starts moving.
before it starts to move? Okay,
So you use that one, the one in kinetic, just solve for theta, because that's the maximum technically.
now, if we ask for the largest angle before it starts to move, are we talking static or kinetic?
Which,
Yeah.
you know, you're not moving, but I'm saying the maximum
The
would
maximum
be that.
static.
So right below that number.
Okay, so here's the deal. It's going to be static because you're at the maximum angle, but when you're at the maximum angle,
It's still not moving.
you're at the maximum static friction, right? Force friction static is less than or equal to mu force normal, mu force normal, but you're at this maximum value, so you're at the equal sign. Then you can go ahead and plug this in here. Does that make sense? And then you're okay. All right? And you can solve for theta because look, if it's static, that's going to be 0, and you can solve this thing for theta. In fact, it's very magical. Look what happens.
Sine theta.
These cancel because that side's 0 now. And you get mu cosine theta equals sine theta, or mu equals tangent theta. It's pretty cool.
That is like that.
Hey, so what if I did this then? What if I stacked up another one on top and I stuck them together so they wouldn't slide relative to each other? And would that change the maximum angle?
No.
That's the new.
Yeah, very nice. Mass disappears, right? So it doesn't matter. You
So
could
they're
set a
tied
truck
together.
on there. It wouldn't matter.
It's
So
the
look.
static.
If you're in a car,
The U of the static.
if you're in a car that's on an incline, hey, actually I've seen
Yeah, it
this.
should be that.
Back home in Missouri, where I grew up, we had an ice storm, and static friction is a little bit greater, or it's greater than kinetic friction, right? So, there was an ice storm, and I was standing out on the side of this hill. This guy had pulled up his car a little bit on a hill and parked it, and it was icy. He gets out of the car, slams the door. Now, there was enough static friction to hold it still, but when he slams the door, it gave it a little jostle, and he popped it past the static friction limit, and then it started to slide down the hill. It slid right through the intersection, right into a parking lot, and ran right into a sign. But it didn't hit anybody, which was great.
Okay, so since we use that solving for f sub s, we use mu sub s, right? For this maximum.
That's correct. You'd use mu sub s. Very nice. Okay, bring in that review packet. Next time we're going to kind of wrap things up before our test next